Bismillahirrahmanirrahim. Dear students, today our lecture is about the order of kinetics. So today we will discuss about order of kinetics. What is first order kinetics? So it can be divided into different parts. First order kinetics, second order kinetics, zero order kinetics. So today our topic is first order kinetic. And first order kinetic mean that whenever the constant fraction of the drug they are absorbed, distributed, biotransformed and excreted for unit times, and these processes increase and the rate with increase in concentration and decrease with falling concentration. So this point is clear. When we are going to increase the concentration of the drug, so the rate of reaction will be increases, while if we are going to decrease the concentration of the drug, so the rate of reaction will be decreases. So it means that how the absorption, distribution, biotransformation and excretion process are mostly occurring at the rates proportional to the concentration of drug in plasma. As we know that, so this graph show time versus concentrations. So look at on the horizontal x-axis, time is given here, and this is the concentration of drug, and this is the graphical representations. So in first order kinetic, the constant fraction of the drug is in the body, so they are eliminated for unit time, and the rate of elimination is proportional to the amount of drug in the body, while the majority of the drug they are eliminated in this way. So I will show it through a different example. Now look at here. This is called first order kinetic. So in first order of kinetics, so they're starting from, so on x-axis, look at here, this is the time, this is the concentration of the drug from 100 to 6.25. So now what is happening here? So as we know that in half-life can be and we have already discussed that the time which is required for a drug to achieve the peak plasma concentration to be reduced 50% half of its original concentration. So it means that after one half-life the concentration of the drug will be reduced to 50%, while after second half-life the concentration of the drug will be reduced up to 25%. So look at the difference, that let's suppose this drug let's suppose a drug which is 50 milligrams, so it means that the concentration of that 50 milligram drug will be reduced to 25 milligram, while in second half life the concentration of the drug will be reduced up to 25%. So after completing the first half lives, so I will mark it here, and this is the total overall, this is the total drug concentrations. Now look at here. So after third half life the concentration of the drug will be reduced to 12.5. So it means that after third half life the concentration of the drug will be reduced from 25 to 12.5, and after fourth half life the concentration of the drug will be reduced up to 6.25. This is in first order kinetic. So this is another classical representation of drug elimination, that how the drug can be eliminated from the body, and the first order kinetic, which is called exponential on arithmetic scales. So look at here, this is y-axis and this is x-axis. This is the graphical representation. So here I have mentioned the time, and here is the plasma drug concentration. So the total amount of the total drug concentration, that is almost 80 microgram per ml. So this is, you can say, I have marked it here 10, 20, 30 up to 100, and then 12, 24, 36, 48 and 16. So I'm going to represent this graph on the basis of half-life of drug in first order kinetics. So let's suppose if the half-life of the drug is 12 hours, so it means that after 12 hours the original concentration drug will be reduced to half its original concentration, and the concentration of drug that is already mentioned here 80. So it means that after 12 hours, so this is the total concentration of drug which is given here. So I will mark it here. So it is 80 milligram for a microgram per ml. So after that, mean after each 12 hours the concentration of drug will must be reduced. So look at here. So the concentration of drug will be reduced from 80 to up to 40 after sequence, after 24 hour, mean after next 12 hour, the concentration of drug will be reduced up to 20%, which I have marked here. And then after 36 hour, you can say the concentration of the drug will be reduced up to 20 milligrams, and after 48 hours, you can say the concentrations after 48 hours the concentration of the drug will be reduced up to 10 milligrams. And then finally after, so you can say after 12 hours, you can say this is the first half-life, this is second half-life, this is third, and this is the fourth half-life, and this is the fifth. So it means that with the passage of time the concentration of drug will be reduced. So it means, look at the graphical representation. So this graph, this is not straight, you can say this show the curve lines, these are curves. It means that after completion of one half-lives, after each 12 hours, the concentration of the drug, the original concentration of the drug must be reduced, and it become 50% reduced half of its original concentrations. Now look at here is the same cases here, area under curve, and which the total exposure to the drug over time. So here this is the first order linear on logarithm scales, and this is exponentials. So it's the same, you can say the plasma drug concentrations that can be mentioned here. So 5 from 5, 10, 20, 30, 40 up to 80, and here this is the time which is mentioned here. So it means that after completion of one half-lives, so it means that the concentration of drug will be reduced up to, so it's the same case. So I will mark it here. This is on y-axis, so I will put here the plasma drug concentration. It means, now look at here. So I have mentioned here that the same dose 80 microgram ml, this concentration, so I will mark it here, so you can touch this boundary. While after that, after the 24 hours, mean the concentrations of the 80 milligram of the drug will be reduced up to 40%, and then so on. After next 12 hours, mean after 36 hours, the concentration of drug will be reduced up to 20%, and then after 48 hours, the concentration of drug will be reduced up to 10%. Mean 10, it become 10 mg, or you can say microgram per ml, depend upon on the concentration of drug. And then after that, after 60, you can say after 60 hours, so mean this is the first half-lives, while this is the second half-lives, while the, and this one is the first, second, third, fourth, and this is the fifth. So it means that the concentrations of the drug will be reduced with the passage of time, but it must be reduced 50% of that original concentration. This is another classical representation of drug elimination, that how drug elimination is occur. So this is the time, and look at here on the y-axis, I have mentioned the plasma concentration of the drug. So look at here, this is also the graphical representation. This is straight, you can say linear equations, and case of first orders elimination, that how the drug is eliminated. So look at here is the same cases here. This is the time, and this is the plasma concentration. Look at here, this is the total mean 5 units, let's suppose after administrations of drugs. Let's suppose this is how much drug will be lost with the passage of time. It mean here in this case the conditions, the dose will not remain constant. There must be a variation occur, and it's eliminations. So look at here, 5 units per hour. It means that after certain period of time, this concentrations, let's suppose if you are going to inject, let's suppose if you are going to administer some drugs in the form of infusions or injections, you can say that is 5 units per hour. It means that after some time, after completion of one half lives, this drug concentration will be reduced up to 2.5 units per hour. And then after this is after second half lives, this concentration must be reduced 50%, so it become 1.25 units per hour. So this is the classical representation. Now look at, if we can compare the zero order elimination and first order elimination, so this will be clear. This is elimination rate and this is the time. So here's it means that the rate of reactions, they are independent on the concentration of drug. So in zero order elimination, let us consider here's, if we are let's suppose if we can administer a drug to the patients, and that is 2.5 units per hour mean that you can say after seconds after first half lives, the concentration of the drug, they remain same, so it become 2.5 units per hour. And then after second half life, the concentration of the drug will be 2.5 units per hour. It means, look at this graphical representation. This is the area under curve, and look at this graph. So it show curve line and this is straight line. So it means that here in this case that the rate of reaction is independent on the concentration of the drug. So in this case, the rate of reaction, this is independent to the rate of concentrations, to the concentration of the drugs. And in this case, in first order elimination reactions, the rate of reactions, this is you can say the rate of reaction, this is directly proportion to the concentrations. So you can say that here this case is dependent. It means that the drug concentration is directly dependent upon on the rate of reaction. So here greater will be the concentration, so definitely it means that the rate of reaction will be faster, and it means that the concentration of drug will be reduced. So inshallah, in my next lecture I will discuss about the zero order elimination reaction, that how elimination reaction can be occurred. Thank you so much for watching the basic concepts of drug elimination, first order kinetics in the terms of half lives of drug. Thank you.